And our next speaker is Bruce Levin from Emory and the E. coli Liberation Front.
Let's see, I don't know. I'm sorry, Jim, I did have a point I should have. What I'd like to talk, well, this is the title. This is the Resistance Collective, and some people you recognize. This is, of course, Mark and Fernando, and these are the various people that are contributed. Today I'm going to be talking in part about the work that Pierre Ancoma has done and Klaus Udeku, if I get to it, Kim Garner and all of these people. So I'm acknowledging them at front, and this research was funded by the NIH, as is probably most research here. The pretentious goals that we have is to develop procedures that will maximize the rate of cure, elimination of symptoms, and prevention of sequelae for acute and chronic bacterial infections. Of course, we want to minimize resistance ascending during treatment and minimize the rate of transmission. So this is sort of the broad goal. Now, there's a whole approach that is being used that I think has to be acknowledged. It's called the rational design of antibiotic treatment. There are whole bunches of people involved. You'd think there would be another alternative, the irrational design, but mostly it's empiric. So it's a rational design versus empiric. And the basic approach is to take pharmacodynamics, and this is the standard picture pharmacodynamics. You pulse an antibiotic, it reaches a maximum level, then of course the concentration wanes, and you have three measures of the pharmacodynamics: the time above the minimum inhibitory concentration, the peak, or the area under the curve. And so that's the pharmacodynamic, that's the pharmacokinetics. And I don't know, PK, I get them right about half the time. This is essentially the primary measure of pharmacodynamics is the minimum inhibitory concentration, and then there are experiments in mice. So this is the sort of approach being used in the attempt to get a rational way of determining dose and so on. Now, one of the criticisms we've had is that these conditions, MICs are estimated under conditions that are optimal for the drug and relatively low densities of bacteria. And the animal treatment experiments usually occur with treatment occurring within hours after infection, meaning that if somebody knew they were going to get infected, they could be well treated So there are varieties of technical problems we have with this. And so over the years, we've been doing both mathematical and computer simulation modeling and experiments with FASTs and chemostats and bacteria and antibiotics. We really believe George Box is right, that is all models are wrong and some are useful. On our website, we have a statement that doing population biology without mathematical or computer simulations is like playing tennis without a net or boundary lines. And so we really feel the models are important. And we also feel model systems are important, but they too are wrong, but some are useful. Now, what I was going to do was give an update of where we are. So I've included some of this because I know these things will be on the website. And so I was going to present the latest work we've been doing and give you only a little view of where we have been. But for reasons that you'll see, I've changed the talk. And I don't know how far I'll get into this update part. One of the things that we've been doing is to consider that there's more to pharmacodynamics than MICs. This is called a Hill function. And it fits, and you'll see it fits quite well. So antibiotics of the same MIC can have very different dynamics. So this is the concentration of the antibiotic, and this is the growth rate or death rate of the bacteria. Above 0 growth rate, below 0 death rate. Minimum inhibitory concentration is the place where the growth rate is equal to 0. And then, as Jim pointed out, we have the phenomenon of persistence. When you do When you treat with an antibiotic, you don't just get exponential kill as you properly should, but rather this leveling off. And I had a whole rant to talk about the latest work on persistence, which I think is very cool, but I've changed it. But this is also, I want to just give you some sense of the fit of Hill functions. This is work with Pierre-Oncoma. This is with Mycobacterium marinum. And you could just sort of see how different antibiotics give you different functions, but they all fit quite well. And not only that, when we estimate parameters, pharmacodynamic parameters, from the Hill functions, we get the right values. So that Hill functions give you a broader view of the dynamics, pharmacodynamics of antibiotics, of very different classes of antibiotics. We've done this with staph, with E. coli, and now with Mycobacterium marinum. And the other thing we've done is show that MICs change dramatically with density. In the case of oxacillin, for example, if you go from the standard 5 times 10 to the 5 to something on the order of 10 to the 8, you're getting a 40-fold increase in minimum inhibitory concentration. So how do you then decide on antibiotic treatment from these optimum things? Our papers go into this, and we rant on and on and on against what we call the PK/PD mafia and their approach. But what I'm going to talk about today, and the thing that made me change my talk, was a recent paper by Andrew Reed, Troy Day, and Sylvia Heiben on the evolution of drug resistance and the curious orthodoxy of aggressive chemotherapy. It just came out recently in PNAS, and we had a little lab meeting about a week ago, and I just sort of said, I've got to say something about this. And unfortunately, well, this is what they're basically saying. First of all, antimicrobial treatment and management practices have pure theoretical and empirical justification for broad-spectrum diseases. They say that medical orthodoxy promotes high-dose treatment and the completion of the course of therapy, even after the patients are no longer symptomatic. And this radical pathogen cure protocol maximizes the evolutionary advantage of any resistant pathogen, which is rather, I think, very important. It's mostly based on equation-free yak-yak. I mean, population genetic hand-waving. But also supported by results of experiments with Plasmodium. And you might think I'm against it, and I will expand on where I really stand. Now, I'm a little bit embarrassed about this, in that, I mean, I almost want to agree with them because I don't want to be among the defenders of orthodoxy. But I find myself with respect to this paper, right in the middle of this crowd of people who I would disagree with more than almost anything else. So I'm going to come out as a defender of orthodoxy, but do so in a way that I think will be compelling. Now, this is our model of antibiotic treatment. We've published it recently, so I won't say much about it. It includes biofilms, that is refractory. It includes persistent cells. It includes dead cells. It includes the resources made available by dead cells. And it didn't include resistance in this thing, nor did it include, as Jim pointed out, the fact that antibiotics are also mutagenic, which comes into this resistance thing. So the kind of theory, and we have essentially periodic treatment with antibiotics, and we have used continuous cultures as a model of sort of an immune-free system to evaluate antibiotics. And I was going to talk about those results, and I may get to some of them if I proceed, but I want to go address the issues of treatment. Now, with respect, as I point out, Hill functions fit pretty well for many different antibiotics. And if we wanted to characterize antibiotics in a quantitative way, if the sensitive are, say, over here, they have a low MIC, so they have an MIC1. We have some say partial resistance, say an MIC2. And we're assuming in this case everything else is the same. We could have different properties. We could have different maximum kills. They all in this case have the same maximum kill, that is -3. And they have different fitness. So that fitness in this case is in terms of the maximum growth rate. So the sensitive have the highest fitness, and the lowest resistant have the most resistant have the lowest fitness, about a 10% fitness cost and about a 5% fitness cost for the intermediate. This is just a model to illustrate some points. One of the points that I'm making is that if resistance in the target pathogen can be acquired by mutation or horizontal gene transfer from the established flora, at the onset of therapy, there will already be a minority population of resistant pathogens. Where we're concerned about the generation of resistance, I'm suggesting that resistance is already going to be there at some low level. And the arguments are that is in this particular example, we have, say, a mutation rate of 10 to the -8 per cell per hour. And if this is the establishment of an infection, you could see resistance emerging and will be there at a low level and will be maintained at a low level. This is a stochastic model, so we have recurrent mutation. So the argument being that if indeed we have somebody infected with an organism for which we can get resistance by a single mutation or by the acquisition of a plasmid that is accessible, then we could almost count at the start of treatment there must be resistance. So that whatever treatment protocol we're designing has to deal with some minority population of resistance. And obviously antibiotics work, so obviously it must be true that we were able to deal with these minority populations of resistant organisms. This and the situation would be more acute if in fact now under some conditions, now the question is what is the dose? Now what I have in this situation is a situation where we introduce antibiotics and they continually decay. Well, in this case they're declining by flow. So every 24 hours, we pulse 5 milligrams per liter of antibiotics, and during the course of that time, the concentration wanes. The sensitive cells, and the sensitive cells have an MIC of 1, and their density is going to decline. So even if we're dealing with 5 milligrams per liter of the antibiotic, that is to say 5 times the minimum inhibitory dose, we're essentially clearing the population of sensitive cells. But we're also rapidly selecting. So we're starting in this case at, say, 200 resistant cells, because as I'm suggesting, resistance must exist. But even if it didn't, it would be generated by mutation under various conditions. Although Mark and I, years ago, before we even knew the word pharmacodynamics, we wrote a paper pointing out that if in fact it didn't exist at the start of therapy, if you treat aggressively enough, it won't have established. I'm suggesting now that if we're dealing with real infections where resistance can be generated by mutation, it exists. Now, if we then increase the dose to 50 milligrams per liter, what you see is that the sensitive are eliminated faster, the resistance comes up more rapidly. Since we're using 50 milligrams per liter, and there is the MIC of the resistant is 50 milligrams per mil, micrograms per mil, really should have been. We're getting some effect on the resistance, but there is really not much difference between these things. So in this case, the dose really doesn't seem to matter in terms of, because the resistance were already there. Under some conditions, increasing the dose can increase the rate of clearance. So that in this particular case, if we have a dose of 25 milligrams per mil, and resistance has an MIC of 10 milligrams per liter, or micrograms per mil, Then, if in fact we increase the dose to 40, where resistance is in fact going to increase at a lower rate, and so that in this case a higher dose is even better. And if we increase it to 50, we can pretty much clear the infection. And or if in fact we have a lower dose and we increase the amount of time, the frequency of administration, we can get rid of the resistance. So resistance, first of all, it has to be considered to be a quantitative character, not just an either-or character. And I'm characterizing it by increase in MIC. But that's, of course, how it's done. There's committees that meet and they decide the break point and they decide what level we have for resistance. So in this case, we have an increase in the dose. Increasing the dose is in fact beneficial for the clearance. So that you'd have to know basically the pharmacodynamics to make your decision about dose. You cannot say increasing dose, simple population genetic theory doesn't work. Now in this case, higher dose treatment can prevent two-step resistance. And in this case, I have something they say a fluoroquinolone, where we have the sensitive, we have a slight increase in MIC for the intermediate level. We have, that is fluoroquinolones, we have two-step resistance. And now we have the high level resistance. If we dose with 5 milligrams per liter, then basically we slowly kill the sensitive, the intermediate emerges, the intermediate is initially present, the double mutant is not present, but once the frequency of this intermediate gets high enough, the double will increase. On the other hand, if we dose with 10 milligrams per mil, then in fact we can clear the infection. So here's another example where high dose is in fact the way to go. Now, the problem with all of this, and as I say, I think it's the greatest limitation of all of this modeling we've done of the within host dynamics of treatment, is we forget the host. In point of fact, we have immune systems. I mean, we could fill this room far greater if we consider immunologists. And so this summarizes all of immunology. They probably would want at least 2 equations for immunology. But anyways, what we're assuming is that in the course of time, we have this whole thing I call the immune system, which then kills both sensitive and resistant bacteria at some rate proportional to the magnitude of I, which increases at a rate proportional to the density of, so that we're saying that the immune system works roughly by increasing, responding to the density. In the simulations, I chose just some parameters, obviously made up, for the half concentration of cells and so on for maximum rate, and the rate of production of the immune system. And I also assume that the immune system doesn't kick in till about 100 hours after things start. Now, so this is what it would look like if we have host-mediated control of antibiotic treatment with an immune system. And basically, in the absence of treatment, we have the sensitive cells, the immune system kicks in, the sensitive cells are cleared. Obviously, that must be what's happening most of the time, and that when we're not treated, we're cured. On the other hand, if indeed we have an immune system with 35 milligrams, we can clear faster. And if we have antibiotics, and we can clear even faster. But there's a kind of curious paradox. Since the immune system is proportional to the concentration of the cells, antibiotics are in a way working against this particular model of the immune system. Is it an artifact? Probably. Now, I'd like to go back and make my conclusions about the assertions. First of all, I think, maybe not great, but I think that there have been some theoretical and empirical justification and some misguided work, but some I think are on the right track. But I don't think the work is sufficient. particularly in dealing with the host response. The medical orthodoxy resistance will be started at the start of therapy. I think this notion of preventing resistance from being there is probably misguided. You've got to assume there is some resistance there. It will be present at the start of therapy. And if it is clear that if the host is cured microbiologically, then treatment should terminate. Obviously, I don't think that's a matter of orthodoxy, it's just logic. And there is more to antimicrobial therapy, the evolution of resistance and so on, than anticipated from naive population genetic theory. There's also more to population genetics in the real world than that. And what is true for Plasmodium may not be true for bacteria. Now, at the same time, having said that, I think we owe them a great debt, because they've brought it up in a very public way that I think will attract more people into the enterprise, which is what we want. Now, I was going to go on and on about what we've done. I will leave this material in the website. You're welcome. We have 3 papers I was going to talk about that are submitted or in press, and you're welcome to everything we have, including, so I'd love to talk to Jim about our persistence work. I hope we have a chance to do that. But anyways, thank you.